You guys, I'm sure, have already heard of Newton and his law of universal gravitation. And I think we talked about the equation that gravitational force is equal to G mass 1, mass 2 over R squared. G is a constant, 6.67 times 10 to the minus 11th, and it has goofy units, Newton meters squared per kilogram squared. And the masses are the masses of two objects, and R, in this case, is the distance between the centers of the objects. The law of universal gravitation says that essentially every particle in the universe exerts this kind of force, this force on every other particle. So there's gravitational force between every pair of objects in the universe. Although generally, like if we're on a planet like Earth, Earth is the most massive object nearby, and so we can pretty much ignore the gravitational force from anything else. Gravitational force is always attractive, which is why sometimes you'll see a negative out in front of this. But again, that negative doesn't necessarily mean you'll plug it into any equation as a negative. It just means that it's pulling toward each other. So if you have object here and object here, the force on this guy from this guy is to the left. Force on this guy because of this guy is to the right. Yeah. So, for example, let's say we have three asteroids, A, B, and C, sitting in a line right here. They're far away from anything else, so they're only exerting force on each other. Let's say A has a mass of 3.8 times 10 to the 5th kilograms. B has a mass of 5.6 times 10 to the 6th, kilograms. And C has mass 8.7 times 10 to the 5th kilograms. A and B, we'll say, are 1.1 kilometers apart. And B and C, we'll say, are 3.2 kilometers apart. Let's say we want to find the force on B. Okay. Well, we can find each force pair just by applying our equation. The force between A and B is equal to G times mass of A times mass of B over the distance between them squared. So that's 6.67 times 10 to the minus 11th times the mass of A, 3.8 times 10 to the 5th, times the mass of B, 5.6 times 10 to the 6th, all over distance between them, 1.1 kilometers, which is 1,100 meters squared. And we can stick that into our calculator. Now, here's actually a point to take note of. Sometimes it can be a pain to punch in all of these numbers in scientific notation into your calculator. But this is a 10 to the 5th, this is a 10 to the 6th, this is a 10 to the minus 11th. So 10 to the 5th times 10 to the 6th gets us 10 to the 11th times 10 to the minus 11th, and these powers of 10 actually cancel out. Sometimes it can be useful to deal with your powers of 10 first. So we just wind up with 6.67 times 3.8 times 5.6 divided by 1100, oops, one more zero, 1100 squared. And we get that the force between them is about 1.17 times 10 to the minus 4th newtons. I'm going to store that. Then the force between B and C, following the same equation, 6.67 times 10 to the minus 11th times 5.6 times 10 to the 6th times 8.7 times 10 to the 5th over 3,200 squared. And again, our powers of 10 cancel out. Let me punch that in. 6.67 times 5.6 times 8.7 over 3,200 squared. And get this is 3.17 times 10 to the minus 5th newtons. Now, we want to know, I want to define the force on B. So the force on C, because of B, is to the right, so I'll call this a positive. The force on A, because of B, is to the left, so I'll call that a negative. So we add those together, or subtract them, I should say, and we get an 8.556 0.69 times 10 to the minus 5th newtons, and it came out negative, which just means it is that to the left. So we can juxtapose forces like that to figure out what the net force is. We can also do this in 3 dimensions. So you had a mass here, mass here, mass here. You know, if they're situated like this, then we have to start dealing with vectors. So let's call this mass A, B, C. Say mass of B is 1.5 times 10 to the 5th kilograms. These are 500 meters apart. Say these are, I don't know, 1,200 meters apart. Mass of A is 1.8 times 10 to the 5th kilograms, and mass of C is 6.7 times 10 to the 5th kilograms. Let's say we want to find the force on C. Well, the force between A and C is G times, mass of A, 1.8, mass of B, 6.7, and they're both times 10 to the 5th, so that's a total of 10 to the 10th, all over the distance between them, 1,200 squared. Okay. You can punch that in, 6.67, 1.8, 6.7, with the powers of 10, and we get 5.586, whatever, times 10 to the minus 6 newtons. I'll store that. Now, if we want to find the force between B and C, well, our magnitude, we got G times mass 1, 1.5, mass 2, 6.7. Together they have a factor of 10 to the 10th, all over the distance between them squared, which is 500 squared plus 1,200 squared. As this hypotenuse would be the square root of 500 squared plus 1,200 squared. And so then when you square that, you just get 500 squared plus 1,200 squared. But this is the magnitude of the force. And if we want to put this into, well, let's get a number for that. 6.67, e negative 11 times 1.5 times 6.7, e 10 divided by 500 squared plus 1,200 squared. And we get 3.966 times 10 to the minus 6 newtons, and I'll store that as B. But FBC we need to break into components. So FAC, the force that A exists on C is going to be to the left. So that's going to be negative 5.586 times 10 to the minus 6, comma 0. There's nothing tricky to do there. But the force on B because of C is going to, or the force on C because of B, sorry, is going to be up and to the left. So there is our magnitude is the 3.96, but then our x component is negative, and that would be equal to the cosine of this angle. Now you could find this angle, but we know just by looking at the triangle that the cosine is 1,200 over root 500 squared plus 1,200 squared. So we can just plug that in there. Sorry, I wrote that kind of small, but that's just this over this. And then, I didn't leave enough space. Then the y component would be the sine, and it's positive because it's going up, and the sine of that is just 500 over root 500 squared plus 1,200 squared. So our x components, we're adding these two together. So we've got 3.96 whatever times minus 1200 over square root of 500 squared plus 1200 squared. And then we are adding that to our 5.56, which I stored as A, I believe. Did I? Okay, good. So you got 1.924759502, 6, and I'll store that as X. That's the X component of our force, 1.92 times 10 to the minus 6. When we add these two together, then we add together our Y components, which is just 0 plus 3.96 times that stuff. 3.96 I stored as B, so we go times 500 over square root of 500 squared plus 1200 squared. And we get 1.52 times 10 to the minus 6. So I'll store that as Y. And then to find the magnitude, we just do square root of X squared plus Y squared. And so the magnitude of our force is 2.456 times 10 to the minus 6 newtons. And if we call this the x-axis, this the y, then that force is at 38.4 degrees above the minus x-axis. So you may have to do some of this vector stuff. And the big reason I do that is because we're going to do a lot more with that when we get into doing electricity and magnetism.